This video will be about section 5.2, which is definite integrals. And in section 5.1, as well as section 4.9, you had an introduction into what an indefinite integral represented and how to calculate one. And that was the area under a curve, specifically a velocity curve bounded by the x-axis. And we use the antiderivative in order to evaluate an indefinite integral. So now what we're going to be looking at is the definite integral. So if we're integrating some function with respect to x, typically we would find the antiderivative, because in this form this is an indefinite integral and we have to add c to the end, some unknown constant. So here what we're going to do is we're going to evaluate it over a specific interval. For example, from the interval a, starting at a to b. So graphically, what this would look like would be some function, and typically that would be the derivative function so that we can find the antiderivative function. So in this case we might be referring to some velocity curve. And then of course we have our x-axis or our t-axis depending on which form of the function we're looking at. And so instead of just finding an infinite area under this curve, we're going to bound it by the interval from a to b. And so now we don't have an infinite region, we have a very definite region going from a to b, giving us a constant for our area. So that's what a definite integral represents. It's the area under the curve from a specific a value to a specific b value, representing an interval. So again, it represents the area under a curve. Over an interval from a to b. So what we need to discuss next is the difference between the net area and the total area. So in the graph that I drew, everything was above the x-axis. So we need to take a look at what happens when we have negative regions of the graph. Well, it's not very straight, but I think we can go with it anyway. So for example, if I have this curve, it's not completely positive. There are sections that are positive. So this region right here, again, bounded by the x-axis. So bounded by the x-axis and the curve. And we get what I'm going to call region A, which is positive. And we also have this other region down here that we can bound by the x-axis and our curve, and I'm going to call that region B, which is negative. So if we put together region A and region B, which is a positive region added to a negative region, we get what's called the net area. However, if I took region A, which is already positive, and I added it to the absolute value of region B, which here we're calling negative, then that would represent the total area. And when we're describing a definite integral, we are actually finding the net area. So we are taking into account negative parts, negative pieces, and we are subtracting them out. So this is similar to a situation where, let's say that you have an object that's moving along the x-axis, and or an object moving along a line in general, and that object moves 5 units in the positive direction, and then it comes back and moves 3 units in the negative direction. And so the net distance would be 2 units away from where you started. So in general, the total number of units traveled would be 8, but the net number of units would be 2. So this is again displacement. When we're finding this net area, we're finding the displacement. So definite integrals are finding the net area. Okay, so let's talk about ways that you can evaluate a definite integral. So let's say you were trying to evaluate the definite integral f of x dx from a to b, where a is the lower limit of integration and b is the upper limit, meaning that over the interval a is smaller than b. So there are 3 ways that we're going to describe in order to evaluate a definite integral. So one of those ways is to use a Riemann sum. And so Riemann sum was addressed in section 5.1, where you take a curve and you partition it into various rectangles depending on how many intervals or subintervals you create, and you find the area of each rectangle by multiplying the base times the height and add them all up. So that's one way, but in general the Riemann sum is an approximation of the area under that curve. So when we create these rectangles, they're not precise, and often there's a little bit of an underestimation or a little bit of an overestimation. But the formula goes like this. The net area is approximately equal to the sum of f of x sub k star times delta x, as k starts at 1 and goes to n. So this basically describes taking all of the grid points, x sub k star. So we take every grid point and we evaluate the grid point by plugging it into the function f. These are going to give us the heights of all of our rectangles. And then the delta x gives us the base of every rectangle, which should always be the same because we are creating equal number of intervals. And those intervals are decided or determined by n, how many rectangles are being created. And then depending on how many of those there are, we go through the sequence of k's. So we plug in k equals 1, k equals 2, 3, 4, 5, however many we have all the way up until n. So that's one way to calculate it. The thing to remember is the more rectangles or the more subintervals, the better the approximation. So typically, we only ask you to do, maybe 4 or 5 different subintervals where you're calculating only a few, definitely a finite amount of rectangle areas. But here, if we really wanted to get an accurate answer for the area under the curve, we'd have to do hundreds, thousands, tens of thousands of rectangles. And obviously that's just not very practical when it comes to doing these calculations by hand. And so really, the area that is most precise would be the area found when you calculate this Riemann sum as n approaches infinity. So essentially an infinite number of subintervals or rectangles. And certainly that is not a practical thing to do by hand. So we could make a good approximation using this method, but an exact number wouldn't be very practical. So a second option is to use geometry. And we'll go over that method in just a second, but essentially we're going to be finding regions bounded by the curve and the x-axis, and we're going to try to break it up into shapes that we know we can find the exact area of, like rectangles and triangles and even trapezoids. And we're going to find the area of each piece in order to calculate the area under the curve represented by the definite integral. The third method is called the fundamental theorem of calculus. And you can tell by its name that it's pretty important. The fundamental theorem of calculus essentially, in my eyes, means that it is the most important theorem that you will learn in calculus. Unfortunately, you have to wait another week to learn it because it's not until section 5.3. But in that section, we will learn how to evaluate this definite integral through a very handy little theorem that someone proved that helps us to calculate this in a very quick, easy way. So in this section, we're going to focus on the first two approaches, and then later on we'll learn what I consider to be a shortcut, which is that fundamental theorem of calculus. All right, so let me show you an example of each of those other methods. So we'll use the same given circumstances and we'll calculate it two ways. So we want to evaluate the integral 4 minus 2x with respect to x over the interval from 0 to 4. So we want to evaluate it. Remember, we want to find the area under the curve bounded by the graph of 4 minus 2x from the interval 0 to 4. So I'm going to write that down. We're trying to find the area under the curve, which is bounded by the graph of f of x, which in this example is 4 minus 2x, a line, and the x-axis over the interval 0 to 4. So what I'm going to do first is create a graph. And the more accurate you can be with your graph, the better. Graph paper is the best way to go for sure. So on my x-axis, I know I'm going from 0 to 4. I'm not quite sure how I need to scale my y-axis yet, so let's do some thinking. So I know I need to go 0, 1, 2, 3, and 4. I need to plot some points. This is clearly going to be a line with a y-intercept at 4. And then a slope of -2. So I'm going to keep graphing. And so my line, when I graph it, looks like this. But remember, I only want the section that's bounded by 0 and 4. So I'm going to draw those boundary lines in. I want to bound my graph over the interval from 0 to 4. I also want to bound it by the x-axis and my curve. So you can start to see these regions come together that we're trying to find the area of. We have this region above the x-axis, which will give me a positive area, and this region below, which will give me a negative area. So let me show you each of the ways that I can find this area.